Welcome to Non-IITian YouTube channel. I am Shorish Goswami and today we will be interested in a problem that inspects the topological properties of the real line and we will show how to find disjoint countable subsets of R. So the problem is this: which of the following statements are true? 1. There exist three mutually disjoint subsets of R, mutually disjoint, each of them have intersection empty, each of which is countable and dense in R. The second problem asks the same question but for any finite number of sets. The third statement asks if there is an infinite family of mutually disjoint subsets of R which are countable and dense. And the last statement, asks if there are uncountably many mutually disjoint subsets of R, each of which is countable and dense. The sophistication increases as we go down each statement. Notice one fact that 4 implies 3 implies 2 implies 1. Well, if 4 is true, then there are uncountably disjoint subsets. Take a countable subset. That proves 3. If 3 is true, if there is countable, take any finite number n, it proves 2. If 2 is true, then just set n equal to 3 and we get 1. However, if a problem arises like this, the idea must be to first attack 4. But that is difficult sometimes. So we will start from one of the ideas to first attack 4. So, however, we will start from 1 and help capture the idea. Statement 1. There exist three mutually disjoint subsets of R, each of which is countable and dense in R. The construction goes like this. Take An is equal to Q plus N root 2. Notice Ai and Aj are disjoint as I not equal to J. Why? Well, without loss of generality, if there exists some x such that x belongs to both of them, that is Q plus I root 2, Q plus J root 2, where I not equal to J, then x can be written as the form A plus I root 2 equal to B plus J root 2. Now, if x equal to a plus I root 2 and equal to b plus j root 2, then take the difference. Take b one side, take I one side. You will get I minus j root 2 equal to a minus b. But the left side is irrational. The right side is difference of two rational numbers, hence rational, which is a contradiction. So they are disjoint. Since ai are translates of q, they are countable. Countable is easy. You can explicitly say what the elements are, and they are dense. You need to think a bit if you are not familiar with this why they are dense. Make a sequential argument. Q is dense, remember that. So any translate of it will also be dense. Just use a sequential argument. That's the hint. Okay. Statement 2 and 3 are similar, proving that. Statement 2 asks for any finite. Statement 3 asks for any countable infinite family. Follow the same construction as statement 1. Take A equal to Q plus N. Remember, while proving statement 1, we did not use the value of n as 0, 1, 2 anywhere. So in statement, as in construction of statement 1, in statement 2 vary n from 1 to n, this is a typo, it must be I from 1 to n. And in statement 3, we let n vary over all natural numbers. By the same reasoning as above, exactly the same reasoning as the above slide, they are mutually disjoint, countable and dense. Statement 4 is where things get interesting. There exist uncountably many disjoint subsets of R, each of which is countable and dense. The same construction won't work there. We are varying over n, which is a countable set. This is where we will mimic the idea of a Vitali set, which any person who has taken a measure theory course is familiar, which is used to construct an example of a non-Lebesgue measurable subset of 0, 1 we know, but of R. Define an equivalence relation tilde on R by x is related to y if their difference is in Q. This is an easy checking that this relation is an equivalence relation. Take the distinct equivalence classes. We know they are a partition of R. Equivalence classes correspond to partition. So you get different partition of class of X, and from each class, equivalence class, pick exactly one element and construct a set N. This set N has this property that every element in R is related by this relation tilde to one and exactly one element of N. Well, uh, why this N is non-empty, this construction can be made actually to very mathematically formally tell it requires axiom of choice, but it's okay. Notice class of any element x is x plus q. This is easy to see. class of X contains Y, then Y minus X must be belong to Q. So Y minus X must belong to Q. So Y is a Q translate of X. So Y belongs to X plus Q. And if and every element of X plus Q is already in class of X. So class of X is countable. Class of X is dense. And since it's a partition, and every class is represented by some element of n, that is, if we take an element of n and take the class, if we take all elements of n and take all class, this comprises every class under this equivalence relation. Think about this if you're not very familiar with Vitali set at first. So union of class of x belongs to n is equal to r. Now n must be uncountable. Why? Class of x is countable, r is uncountable. So if n was countable union of countable sets is countable. So n has to be uncountable. So we get an uncountable set, and our required family is Ax equal to class of x, that is q plus x, where x belongs to n. This is an uncountable family of dense countable subsets. That's okay. So that each of them is disjoint. Now, if you are not, these are equivalence classes, so they will be disjoint. But if you are still not convinced, think in this way. If Ax equal to Ay, or if Ax intersection Ay has a common element, then there exists some A plus X, where A belongs to rational, is equal to B plus Y, where B belongs to rational. But X minus Y are not related, so X minus Y do not belong to rational. Using this, develop a contradiction. So this was a rough idea of how all the statements follow. Hence, all four statements are true.